Imagine this scenario. You're pushing a stalled car and you can feel the force you're applying to move it. But did you know the car is pushing back on you with an equal force? Forces are always a result of interaction and they exist in a balanced pairs. In this activity, I'm going to show you about the balance pair of this interaction force and about a way a string transmitted force. Also, we'll investigate the tension in the string, the function in a simple pulley, and a simple tug-of-war procedure.
So before we start the experiment, these are the materials needed: a pulley, string, spring scale, and 500-gram hook masses. Now, let's start. Step 1. Suspend the 500-gram load from a string that is held by a spring scale as shown in Figure A. Step 2. Drape the string over a pulley such that both ends of the string hang vertically as shown in Figure B. Hold the scale steady so that it supports the hanging load. Step 3. Move the spring scale first to a higher, then to lower position, keeping the string on each side of the pulley vertical. Move the spring scale to various angles to the vertical until the scale is horizontal as shown in Figure C. Remove the string from the pulley and drape it over a horizontal rod. Repeat step 4 as shown in Figure D.
The scale reading tells us that the tension in the string is equal to the weight of the hook masses. Comparing to the weight of the load to the scaling reed, there is nothing changing because it is still equal to the weight of the hook masses. Comparing the tension with the string, the scale reading is equal to the tension in the string. The reading is still the same at the higher position. Even the scale to a lower position provided the same result and it's not changing, it is because the tension does not depend on the position but on the force transmitted by the string. The scale reading is still the same, as it moves the spring scale to various angles to the vertical. Until the scale is horizontal, the scale's reading does not change. Knowing this is the pulley serves only to change direction of the force. In this scenario, friction between the string and the rod plays a significant role. This friction opposes the movement of the load and causes a difference in tension between the two sides of the rod. The force of friction counteracts the sliding of the string, effectively contributing to the support of the load. As a result, the tension on the side of the string held by the hand is reduced. When you exert a stronger downward force to lift the load, the tension on the sides held by the hand becomes greater than the tension on the load supporting sides. This difference in tension is precisely equal to the frictional force between the rod and the string, which plays a pivotal role in this interaction. Based on the data, all different step outcomes are the same or constant. There is no change in mass as the spring case goes in any direction. The pulley does not change the magnitude of the force, it merely changes its direction, facilitating the upward or downward movement of the load. The experiment findings confirm that the pulley did not affect the tension in the string. The tension remained constant and equal to the weight of the load throughout the experiment, regardless of the position of the pulley or the angle of the string. This aligns with the concept that every action, the weight of the load, results in an equal and opposite reaction.